So what are data-dependent shapes? So data-dependent shapes are whenever you have an output tensor whose size depends on the actual input data in the tensor in question. So for example, with something like non-zero, the size of your output would be how many non-zero entries you have in your tensor. Even something like padded sequence from our old RNN days is data dependent in this way because the size of your output depends on how much padding you had, because that's everything that was deleted in that case. Another example of when you have data-dependent shapes is when you have some sort of number that represents a size in question. So you might just take that size out using item or toList and create a tensor of that size. But you might also, for example, have an operator like repeat interleave, which takes an input tensor and then duplicates it however many times the repeats are in question. So these are all cases that can cause data-dependent shapes. All right, so I gave you the definition of data-dependent shapes, but I didn't really say why you might want to have data-dependent shapes. Well, there are a whole lot of use cases, many of which I talked about in my dynamic shapes talk last year at PyTorch conference. When you have recommendation models, when you're doing your embedding lookups, you don't know which server you need to send your actual record to in question. Depending on what sparse features the users have, they may go to one server or another. So the exact number of queries you're going to query on any given embedding table is going to differ from server to server. Or take, for example, when you're doing transformers. You may have a situation where your sequences are very similar in length, and so you just pad them out. But you might also be interested in only using as much compute as you need for the actual lengths in question. And you don't actually want to waste space on extra padding tokens at the end. If you're doing some sort of object detection segmentation, it's pretty common for your bounding box to be variable in size. And then you only call ResNet on the actual region of interest. And of course, when you're doing pre-processing, a lot of the things you might want to do are like deduplicating duplicate features. And that's something that you want to actually look at the data to figure out how much processing you actually do. The overall theme of all of these things that are going on is that the data is influencing the compute you want to do. You can always do a fixed amount of compute on all of your input data, and you'll know exactly how much compute you need to do. But in a lot of cases, there's a lot of sparsity you can take advantage of. There's some deduplication you can take advantage of. And so if you pay for actually going ahead and only looking at the things you care about, you can actually get a big compute efficiency win in this case. So, why not data-dependent shapes? Well, to actually look at the data and to find out, how I can take advantage of the sparsity, I have to actually do a device-to-host sync. I have to wait for the GPU to give me the data so that I can actually look at it and say, oh, this is how many non-zero elements are in it. And that's really bad because when you are normally running your programs, your CUDA execution can run ahead of the CPU host because you don't really care. You're just launching things, but you're always doing the same things. The whole thing about compute efficiency is you want to do something different on the host side depending on what data you have. And that makes it kind of different. So, Horace always tells me, is there some other way you can do it so there isn't a device-to-host sync? But sometimes it's just not possible because, one, you're lazy and you just, put in an item call because you didn't know how to, bludgeon PyTorch into doing the right thing. Or maybe you actually really do need to take advantage of your compute sparsity. Like in recommendation models, your features are really, really sparse. So you're just going to be in a lot of trouble if you actually try to pad it out. It basically is not possible. So this talk is about data-dependent shapes in PT2, the new compiler stack that we've been working on in PyTorch. And so what's the problem with data-dependent shapes when you're working with the compiler? Well, remember, PyTorch 2 is a tracing compiler. Our whole goal in life is, with some exceptions, to generate a straight line trace through your program, which we are actually going to compile for compilation. So normally, Python programs have all sorts of if statements, they have all sorts of error checking, and we need to figure out how to actually, thread the needle through a single path that we're going to pass to our compiler. And ordinarily what we can do is we can just look at the real values in question and use that to figure out, well, I'm just going to, figure out what the real data says I'm supposed to do, and I'll go down that path, and I'll install a guard to protect me against, cases where that situation may not be true. But when I have data-dependent shapes, I don't know what compute, which way I'm going to go, because I have no data to peek at, because I'm the compiler, and I haven't even run the tensor compute yet. So I'm in trouble. So I have to decide which way I'm going to go, and to do that, I need you, the user's help, to tell me about it. So, in some sense, like the programs we want to trace and compile are fundamentally traceable. They are only really doing one thing at any given point in time. If I'm doing an embedding lookup on a bunch of embedding servers, like maybe I may have more entries to look up or less, but I'm still doing the same thing in each of these cases. So if your model has this fundamental structure, or even if it doesn't, and but it's a very localized change in behavior, you hope that you can compile it. And the purpose of this talk is just to talk a bit more about how exactly you can do that. So to do this, I first need to talk a little bit about how dynamic shapes are implemented in PyTorch 2. So first, I want to recap how normal symbolic reasoning in PyTorch 2 works when you have dynamic shapes. So let's say that you have some input and you want to make it dynamic, so you don't know if it's going to be size 8 or 16. You want to generate a single compiled graph which works in all sorts of situations. So what we do is we assign this a symbolic variable. We say, okay, we are going to give this, say, S0, which we can fill in with some other value. But we remember what the actual value was. Because PyTorch 2 is a just-in-time compiler, we always have the actual inputs at hand. So I can remember that S0 had value 30. Then, when I do shape computation, when I add to it or cat it together with other things, I represent this arithmetic symbolically. And then when I'm tracing, if I have to answer a question about do the sizes match? Am I bigger than 20 or less than 20? All I need to do is generate a guard, and the guard is computed off of the real values. I take my real values, I put them into the expression. I see, oh well, 30 doesn't equal 450. So S0 equals 450 should be false, and that's the guard, and I go ahead and keep going. And sometimes, cherry on top, I can prove that I don't need to check this again at runtime because I've already checked the same thing over again, and there's a little bit of optimization to deal with this case. Let's contrast this with what happens when you have data-dependent shapes. So a data-dependent shape is characterized by the value of this number is computed at runtime when you do the tensor operations. So when I'm a compiler and I'm compiling things, I don't know what this value is. So we actually, the way we implemented this, we said, okay, well, an unbacked cement, a cement that is missing the real data, is simply one for which we don't have a hint. We don't know what its value is. Now, there are still some things we can do with these. If we do error checking, we can, we don't really care what the value of the unbacked cement is because an error check always has to pass for me to do something useful with my program. So, we'll just go ahead and add a runtime assert to check this, later. But I don't need to know at compile time if this expression is true or not because I know it is true because otherwise I would have raised an error. But if I hit a conditional, if I need to do something different depending on if a value is 450 or not, now this previously what was an optimization, if I already knew this was true, this is now load-bearing. I must be able to statically prove that this condition goes one way or another. Otherwise, I have no idea which way to go, and I will fail with a guard on data-dependent error. So we have to look a little bit more at what this statically known to be true or false algorithm does. And we put some stuff in it, but it's actually, at some fundamental level, a very simple solver. It's not like something like Z3, where we're doing very complicated stat solving to solve things. So we have some axioms. Those are just the things that we already know to be true, things we've already guarded on, things that we've done error checking on. And then we have some expression, and we want to know if it is true or false, or maybe we don't know, and we're just going to raise an error in this case. We have three main parts of the symbolic reasoning that we have. This is not the law of the land. This is just contingently what we've got so far. So we use SymPy to do symbolic reasoning. SymPy has plenty of symbolic simplifications that make things simpler. We will check if your axiom actually says exactly that something has been evaluated. And we have a little bit of fuzz, so if you say something is less than something else, we also know that they're not equal. So we can do minor implications like that. And finally, and the most important analysis we do, is we have a value ranging. range analysis. So every value that we have in our program has a lower bound and an upper bound, and we can use this to solve questions about inequalities. So for example, if I have a expression like, does u0 times 2 plus 1 equal 0? If I assume that u0 is some sort of size-like quantity where it's greater than or equal to 0 and unbounded from up top, then I can do a value range analysis where I instead interpret this expression in the abstract domain of value ranges. And so I say, okay, well, when I multiply it by 2, my value range doesn't change. It's still greater than or equal to 0. But when I add 1 to it, now I know that it cannot possibly, the resulting expression cannot possibly be 0. It has to be 1 to infinity. And now I know that 1 to infinity is disjoint from 0, and therefore this must be false. And I can discharge this proof obligation there. So your sort of main tool, in some sense, is, hey, whenever the compiler asks you, should I go left or should I go right? You can simply tell it, hey, you should go left by just saying, hey, I'm going to assert that this expression is true or false, depending on what the case may be. And you don't have to line it up exactly because there's a little bit of reasoning we do, but for the most part, this is your bread and butter, how to get past guard on data-dependent errors in the program. So this got us pretty far, and then we ran into some problems where we actually needed to make some changes to the framework in PyTorch. And so that's the next thing I want to tell you about, is this idea of size-oblivious PyTorch. So the way I'm going to ease us into this is I'm going to look through some examples in PyTorch's eager API of sort of strange behavior that happens that is kind of unintuitive. So in this example, I have a program. I'm creating a b by 20 by 1 tensor. It's filled with random data. And then I'm calling squeeze on it. So for those of you who don't remember, squeeze is an operation in PyTorch which removes every dimension which has size 1. So this is just a convenient thing to do sometimes when you're trying to get something into the right shape to pass it somewhere else. So the question here is, what size tensor do I get in this case? And so the obvious answer is, well, you should get a B20 tensor, a 2D tensor, because I'm just going to chop off the last one dimension. But there's a caveat, and the caveat is when your batch size is 1, actually you end up with a 1D tensor with only size 20. And the claim I'm making here is that this is actually kind of strange. Probably if you were writing this code and you use squeeze on it, this would actually probably be a bug. And the way you would fix this bug is to tell squeeze exactly which dimension you wanted to get rid of, so you wouldn't accidentally chop off the batch dimension when it was 1. Okay, so something weird here. Here's another example. So here I create a tensor of size b, 1. And I then expanded it into a b by 100 tensor. So expand is a cool op. What it does is it sets the stride on the last dimension to be 0. So I don't actually have to create a new tensor with this huge size. I just look at the same value over and over again. And this look at the same value over and over again behavior means that the result is not contiguous, because a contiguous tensor is one which you don't have to do anything funny to read out the actual data on it. But there's an exception. When b is 0, the resulting tensor is contiguous, and it's contiguous for a very dumb reason. It's because, well, if you have a 0-size tensor, then it always is contiguous, because there's nothing to tell you that it's not contiguous, because there's no elements. And that's just how PyTorch defined contiguity. One final example, let's say I'm adding two tensors together, two 1D tensors. One has size S0, and the other has size S1. I add them together, and should do the sizes match for the two tensors? And once again, the answer is yes, except when one of the sizes is 1, in which case you do broadcasting. So I really can't figure out anything in this situation. So the whole point of this story is that there's something kind of strange going on here, right? There's a bunch of semantics in PyTorch where we do something a little strange when you have dynamic shapes, where intuitively you didn't want PyTorch to do something different just because the batch size happened to be 1, but there's really no way to distinguish between 1, the constant that I want to treat specially, and a dynamically sized variable that happens to be 1. But in the case of unbacked semantics, when we're trying to compile a program, this distinction is very useful because what I want to do is I want to say, well, when I have some value and I have no idea what it is, I just want to, pretend that it is not 0 and 1 and, unlock this strange parallel universe of PyTorch, which actually I think is much more intuitive than the regular eager mode universe. So when you have size-oblivious going on, we'll assume that the size variable in question is not 0 and that it is not 1, and then we give all of the intuitive answers for these cases, even when you would possibly at runtime have these special case values. So when I want to do these alternative semantics in PyTorch, I have to make some changes to the framework, and the general recipe for these changes is that whenever I have a test in the framework, testing one of these things, and I want to change the behavior depending on if I've got a size-like unbacked cement, I can do one of these guard size-oblivious things. And what this says is, please drop me into this alternate universe semantics when I am tracing unbacked integers, and treat it as if that those integers are strictly greater than or equal to 2. And so, for example, in this example, going back to the expand example, how do I know what the value of this expression is? Well, if I'm running this on a U0 by 100 tensor, the number of elements is a symbolic expression U0 times 100. So U0 is size-like because it's a tensor size. Because I'm in a size-oblivious test, I will assume that it is not 0 or 1. So I end up with a value ranges that U0 is greater than or equal to 2. And so when I multiply by 100, I know U0 is, there's a typo on this slide. I know U0 times 100 is greater than or equal to 200, and therefore this quantity is definitely less than 2. I do not short circuit on this line of the program, and then later I discover that, oh, because one of the strides is 0, this tensor is not contiguous. If you didn't catch all that, that's okay. The main point is that we do have this alternate semantics for unbacked semantics, but it's basically what you expect. Last year, I did talk about this thing called unsound 0-1 specialization. The difference is that we used to apply this idea of the size is greater than or equal to 2 everywhere, and now we only apply it at spots where we have specifically said we want to change the semantics of PyTorch in this case. So if you have something like hand tracking, where you actually do need to distinguish between having 0, 1, or 2 hands, then if you didn't put a guard size oblivious on it, we will not assume, oh, you always have 2 hands. And you can find out about that, get a guard on data dependent exception, and then figure out what to do. I'm going to skip these slides. So finally, what I want to leave you with is a recipe for compiling and exporting models that have data dependent shapes. So the way that I like to think about the compilation process when data-dependent shapes are involved is you are kind of in this twisty maze of a lot of passages. And every time you make some progress, you hit a branch in the path. And then you have to decide which way to go. Maybe there's only one of these when your model is very simple. There could be a lot of them. And that's happened as well on some of the models that we've worked on. And so it's really nice to first get a lay of the land. First, look at the cheat code. So there's a config option in PyTorch, fake tensor propagate real tensors. Well, just go ahead and do the trace with the actual real tensors along. And so every time there's a point in the graph, your real tensor will, whisper in your ear, oh, well, on this particular value of the tensor, this expression evaluates to the left. And you can just go ahead and follow it, get all the way to the end, and find out how many things you need to fix with your program. And so you'll get these logs, and you'll see this log tells you, hey, there's a runtime assert for this thing. It also, you can even ask the program, tell me more about this assert. What was the exact backtrace that triggered this guard one way or another? Once you figure this out, you can then resolve your problem into, okay, now I'm going to one by one fix each of these problems, and figure out which way I need to go in one place or another. And there are a number of different fixes, which I'm going to step through. The magic of this process, and something that I've also found very useful when we've been working on these, is you don't have to understand the model at all. The system will tell you exactly where the problem is, and it'll say, hey, please tell me what to do. And you don't have to know what the model is, you just have to locally reason about what you should do in that position, fix it, and then you can move on to the next one. And you keep doing that until you're done, and we have plenty of cases where people have, they have no idea what's going on in the model, like me, and then they get to the end and they're like, hooray. You just need to know enough to solve individual problems. So for example, you might ask yourself, do I actually need this branch on the expression in question? So I have a number of examples here, but the one that I want to mention here is there are a lot of functions where you take an optional size argument. So if you pass in the size argument, we'll allocate your output based on that size and write things into it. But if you don't pass in this size argument, we will compute it. But that computation of the output size is data dependent because there's maybe some list of lengths. I'm going to sum it and pull out the item. So something that happened a lot with models we worked on is people would just forget to pass in the size, which they knew, into these functions, and then they would be doing this data dependent compute, and there would be unbacked cements. But it turns out you can just pass in the size, and then there's no more data dependent compute. This is great, right? The best way to deal with data dependent shapes is to not have them at all. And by the way, your model gets faster too because you're no longer waiting for the device to host sync. Another thing you might ask is this condition always true or false? One of the common situations this occurs is when our symbolic reasoning is not strong enough. We're very dumb. So you might look at that expression that it's asking you about and say, actually, I know this is always true. And so you can just tell us about it by adding a torch check to your program, and then we will just always go that way. And you don't have to worry about getting it wrong either, because we will add a runtime assert. And so if at runtime, when you're testing your model, it turns out you were wrong, we will in fact give you an exception so you can look at it in more detail. Another question is, maybe this conditional should be true or false. And this is the sort of size-oblivious idea. Unfortunately, usually this is there's some code in PyTorch library that needs to be patched. Sorry. You should be willing to patch PyTorch code when you're working on this sort of thing. We're very happy to accept GitHub issues and pull requests, so do send them our way when you think it's this sort of situation. Another situation is when the branching is local. You need to look at the data and do something different depending on it, but it's a very small segment of your code. And so maybe that segment of the code isn't important to pass to the optimizer, so you can just wrap it up into a custom operator so that you never see that there was a fork in the road in the last case. And finally, maybe you can use torch.conf, and torch.conf has a number of restrictions. You have to actually, return the same tensor size at the end on both branches. You can't have side effects in the branches. You can't pass out views of the inputs and the output. But assuming you work out all of those things, this can be get out of jail free card for when you actually do need to do something different at runtime in your model. So I have this nice case study. We were working on a recommendation model at Meta. We wanted to export it. They wrote I didn't do this one. It was a bunch of other people. They wrote this really nice journey log with all the problems they had. 3 of them where they ran into bugs in PyTorch that they needed to fix. Oh yeah, I highly recommend running nightlies if you're sort of in this regime. So we fixed those bugs. You don't have to worry about them. There were 7 cases where they needed to make changes in the model. Some of them were the ones that I told you about already. And then there were 19 other non-data dependent related problems. Sorry, export is hard. It's kind of life. All right, so in conclusion, it's been a really long journey. I do feel like I'm kind of repeating myself over again. Last year, I gave a talk about dynamic shapes. Now I'm giving a talk about data-dependent shapes. Has anything changed? But we have put in a lot of work. We have fixed a lot of bugs. One of the really big changes is we redid how inductor code gen for data-dependent shapes works. Horace had another story for me, which is that he was trying AOT inductor with data-dependent shapes, and it just worked the first time. And I was like, well, I did fix that, but it was kind of surprising that we hadn't actually tested this, but it did work. But it's just really unusual to be so committed to data-dependent shapes, because most ML compilers are just so stuck with static shapes that this is just like, they can't even begin to like approach the problem of how to deal with data-dependent shapes. So we are really the only game in town if you want to deal with this sort of thing. And I think it's really important for PyTorch, because why do you like PyTorch? You liked PyTorch, eager mode PyTorch, because it was so simple, it was so flexible. You just wrote the code you wanted to write, and it just worked, right? And when we went into the compiler world, sorry, like, yes, the compiler is buggy, sometimes it doesn't work, but the like ethos of the compiler, which we are going to keep improving on, is that we will take your code as is, and you can get the wins when you want them. And so supporting dynamic shapes and supporting data-dependent shapes is an important part of our strategy of making sure that your eager code will also run with compile. So I'm going to leave some time for questions, and thank you all for listening.